last week we talked about the basics of heat transfer and how heat travels from objects that are warm to objects that are cold, and one will release energy and one will absorb it, kind of in this relationship between each other, following the law of conservation of energy. And so we're going to use that concept today in partnership with calorimetry, which is just a fancy way of saying containing heat, in order to do some calculations. And we also have our little equation here, Q equals MCAT, that we derived on Friday from the units of specific heat. In our lab, we used it in the form that C equals Q over M delta T. But if you arrange this to solve for Q, which is our heat transfer, then you get Q equals MCAT. So there's our equation used to solve any type of thermochemical calculations where we can solve for heat, mass, change in temperature, starting temperature, final temperature, or a specific heat like we did last week. So just like we've talked about previously, the Q is energy measured in joules. The M is mass measured in grams, and delta T is the temperature change in degrees Celsius. That little triangle means delta, which is a change in temperature. So you will not plug in a starting or an ending value. You'll actually plug in the difference between the two. And when we do the difference between the two, sometimes we will specify this as the final temperature, TF, minus the initial temperature. It's just breaking down what you're actually doing when you find the change. You take where it finished, subtract where it started, and that's your change in temperature. Then C we've already talked about in depth last week. This is the specific heat, and it has kind of that combo unit that relates them all in joules per gram degrees Celsius. Now, when we're working with heat, all heat released from a sample or from the system is absorbed by the surroundings, as long as our heat is contained. Okay. And we can contain it using a device called a calorimeter. Okay, so the significance of a calorimeter is that it will allow us to surround a sample with water, and then using the heat change of water, be able to figure out some information about the sample itself. Since we can measure the mass of the water, there's our M. We can measure the temperature at the beginning and the end of the water, there's our delta T. And we know the specific heat of water, which we are going to talk about in this last box for our vocabulary, that we can always plug in for C. We don't have every value of every sample memorized, right? But water, we can memorize its specific heat and then use that to get other information. So our calorimeter can be really helpful when we use our system as whatever we drop into the calorimeter, and then the surroundings is the water. So that amount of energy released by the metal or the reaction that you put in the water, it's going to be the same that the water absorbs, the same amount of energy. A calorimeter is kind of like a thermos. Let's see if I can get my pen to work here. So that none of the heat will leak. So when we're measuring temperature change, it will be a true relationship to the heat absorbed. There's none that will just kind of go out into the room because of the way that the calorimeter or this container is designed, so that heat does not get out or get in. It'll have a barrier so that it cannot escape and affect our results. So when we use a calorimeter, just like I said before, all the heat released from the system is absorbed by the surroundings. If you want to replace surroundings with water, that's what our calorimeter would be. And then we put a sample in. So if you look at example 1, this is an example of a really basic calorimeter that you could make. Actually, both of these pictures in example 1 and example 2 are simple calorimeters. They are not perfect, but they do the job. So this is 2 styrofoam cups, and styrofoam cups are pretty good at containing heat, which is why you can hold, scalding hot coffee and not feel it through the styrofoam, and it will stay warm for a pretty long amount of time, especially if you put a lid on it. So our surroundings here is going to be the water, and our system is the metal. And so all of the heat transferred out from the metal, because it's going to be hot, conducting heat out, the water is absorbing it. And so the water's temperature is going to increase as the sample is introduced. And that will give us a relationship between the amount of energy that the water absorbs that has to be equal to the amount of energy that the sample gave off. And last piece of helpful information here is the specific heat of water. It can be used to determine the energy absorbed. So our units, just like we've talked about, of specific heat are joules per gram degree Celsius. And you actually calculated this last week. That water is 4.184 joules per gram degree Celsius. And if you had different units of specific heat, sometimes calories are used instead of joules, that would be 1 calorie per gram degree Celsius. But really, overall, we're going to be using 4.184 joules per gram degree Celsius as our primary specific heat for water. So let's try a couple of examples and see what we can figure out about this metal in example 1. So it says a piece of metal weighs 59.05 grams. There's our mass of the metal. And it was heated to 100 degrees Celsius. So there's our starting temperature for the metal. So initial is the I, Ti of the metal. And then you put it in 100 grams of water. So there's our mass of water. Initially at 23.7 degrees Celsius. And then they both come to this final temperature. So this is going to be TF for both. I'm going to box everything that's about the metal and then circle everything that's about the water. Circle, circle, and that one's going to get both because it's referring to both. Okay, so when we do our equation that Q equals MCAT, we're going to use only the values that talk about the same focus, whether it's the water or it's the metal. So let's start by writing our equation, Q equals MC delta T, and we are finding the heat. So calculate the heat transfer, that's going to be Q. And this says from the metal to the water. We do not have a specific heat of the metal, but we always have the one of water, and that's why calorimetry is so powerful, because we can always focus on the water first and then work kind of backwards to figure out more information about the metal. So we have a mass of water, which is 100 grams. We also have the specific heat, always 4.184. And then we have a starting and an ending temperature. So if we write down this as a subtraction problem for our delta T, there's our information. And that comes to be a heat change, if you pop that in your calculator, of 4.1 degrees. Again, remember, we need the change in temperature, not just the starting or ending value. And then once we do this multiplication, that final product is the energy. Ta-da! So 1,700 15 joules for the sake of significant figures here. Okay. Now we can, like I said before, work backwards to figure out more information about this metal. We have the metal's mass, starting temperature, and ending temperature, and now we also have its heat transfer, because remember we've talked about heat transfer absorbed by the water in a calorimeter has to be the amount of heat also released by the metal. So we can use this amount of heat we just calculated as Q when referring to the metal as well. So now this time we're going to solve for specific heat. Calculate the specific heat, that's C, of this metal, and determine its identity from the list. We can do that because, like we talked about last week, specific heat is a property that is intensive, so it's going to be about its kind of identity, and it doesn't change based on the substance. It will change based on, or the amount of heat required will change based on mass and things like that, but not the specific heat itself. So that's what we're going to solve for, is C, using the mass of the metal, which in our previous 59.05 was what we boxed for mass of the metal. Then we have C that we don't know. And then we have another temperature change ending at 27.8 and starting at 100. So this little subtraction problem is actually going to give us a negative number because it's a release of energy. And if you subtract final minus initial, that will show you your energy here is released, and that should make sense for the metal because it's just really just telling us that it started colder or started hotter than it ended, or went down in temperature. Now let's solve for C. If you multiply 59.05 and 72.2 and then divide them over, so do your math. I'm just going to put them both over here. You want this product. Okay, and that should give us C. Just going to erase that. Okay. Rearranging our equation. Now we have something that looks really familiar to last week. Joules over mass times temperature change. And we plug it into our calculator and we find that our heat released and our temperature change, this is going to give us a specific heat value of 0.402 joules per gram degree Celsius. So if we look at our list of options, this matches brass. Therefore, we have figured out that this sample is the metal brass. We're going to do a part 2 video for some food calorimetry, where we find the energy burned or the calories in a sample of a peanut. So tune back in for part 2.